Okay. Good afternoon, everybody. Can you hear me? So it's a truly great pleasure to have Professor Senthil come here and deliver these series of Chandrasekhar lectures. And I welcome you all for this series plus the discussion meeting, actually, which has already begun since yesterday. So before I proceed to have Kedar introduce Senthil and Professor Ramakrishnan present you a memento, I'd like to take a few minutes to tell you about what we are and what we are doing, that is the ICTS. So the ICTS was established in 2007, and it's an exciting new adventure in Indian science. Okay. And its aim is to catalyze a transformation in the way we do research and also education in the basic sciences and mathematics. So that is the mission, the main mission. And the idea is to go about doing it in the following way. So ICTS combines high-quality visitor-driven programs of varying duration with top-notch in-house research in various areas of the theoretical sciences, with the aim of creating an interactive and participatory environment of research in the basic sciences. The programs have both educational and research components and contain embedded conferences. So one such program is the one you're having now, which I'll elaborate on a bit later. Okay, so the other thing is, besides visitor-driven programs of various types and length, we have decided to develop a very strong in-house research component. Small but very strong and top-notch. So the research component is organized as a union of families of researchers. And ICTS is envisaged as a center with a permanent faculty of very modest size, but of the highest quality, together with a large floating population consisting of visitors, postdoctoral fellows, graduate students. There's also, of course, a huge support from associate faculty members who spend a few weeks at ICTS every year or interact with in-house research groups on a regular basis. So this is all this is really happening. This is not being envisaged. It's all happening. And the current areas of research at ICTS are in the area of astrophysical relativity and gravitational wave analysis, data assimilation and dynamical systems, especially in the earth sciences, statistical physics, condensed matter physics. These are the more traditional ones, string theory, quantum gravity, and physical biology and interdisciplinary mathematics. So this is an area which we have been all very keen on. And finally, we have an outstanding young scientist who is an alumnus of this institute, actually, who has just joined us. And we are growing this unit also. We are very keen on interdisciplinary mathematics. I don't want to elaborate on exactly what we mean, but I can talk to you later on. Now, programs. So the programs provide a platform with resources for researchers to meet, and during these very high-quality programs of various durations. And in this way, we strive to incubate new and emerging areas of research. See, this is one of the goals, actually. We'll get there someday. And also, cross-disciplinary immersions are encouraged at ICTS within the faculty and also within the visitors program. And the programs contribute to transforming the way people do research. They ensure a participatory involvement of students, postdocs in this process. This is very important. And they explore new directions in science, foster important research areas, and build a platform for theory to encounter experiment. This is rather important because our name actually has theoretical sciences, and many times I have been sort of advised by people I won't mention in the government that why do you have theoretical there? Just remove it. But then I said, you have to give me more money. Okay, so since 2007, ICTS has organized 95 programs and 26 discussion meetings, which has made substantial impact on the Indian science scene. Okay. So besides the regular programs, we also have 3 named series after Subramaniam Chandrasekhar, Srinivasa Ramanujam, and Alan Turing. And we first started with the series in physical sciences because ICTS was born from physicists, you see. So there have been very, very interesting Chandrasekhar lectures right from the beginning. Then we have the Ramanujam series, which is for pure mathematical sciences, okay. And the Alan Turing series, which just got inaugurated last week in the Indian Institute of Science, just across in the biology auditorium. So today, before I mention about the lecture today, I just wanted to say that presently the ICTS is actually located just down this road in the old TIFR center until it moves to its new campus in North Bangalore, that is in a couple of months. And this is a world-class residential campus designed to provide office space and on-site accommodation for more than 150 academic members, including 75 visitors. And this is the Chandrasekhar lecture of today. Let's see what is over here. Sorry, I think the slides got a bit interchanged, so excuse me about that. But this is where we are located. This is the Indian Institute of Science over here. And this is the ICTS. This is the NCBS. This is the JNCASR. And this is part of the academic ecosystem of North Bangalore. So here are some photographs of the ongoing construction, which is almost 80% done. And when it finishes, it will look like this. And it's already starting to look like this without the foliage, of course. So I think I'd like to thank finally T. Senthil for delivering these lectures in spite of some personal issues, and also Kedar and Subrato for organizing this discussion meeting around these lectures. And of course, I'd like to thank all of you for your presence over here. It makes it an exciting event. Thank you. So with these few words, I'd like to invite Professor Ramakrishnan actually to present a memento to Professor Senthil. Come. So this is something we do. Come. Oop, be careful. Professor Ramakrishnan. What is inside? No more. Thank you. And now I'd like to invite Kedar to introduce Senthil.
Do I need a mic?
Yes, here it is.
No, it's fine. So it's my privilege to introduce today's Chandrasekhar lecture speaker, Professor T. Senthil. Senthil received his initial undergraduate training at IIT Kanpur, and he belongs to this long tradition of fantastic people who have graduated from that institution and gone on to academic careers all over the world. After IIT Kanpur, he went to Yale to work with Subir Sachdev and wrote a thesis on disordered strongly correlated systems. After that, he had a fairly long postdoctoral stint at Santa Barbara, where he did many interesting things, including gauge theories for spin charge separation and the theory of disordered quasi-particles in unconventional superconductors. He then moved to MIT, where he has been on the faculty now for about 15 years. He holds a distinguished visitors chair at at the Perimeter Institute, and he's a Simmons investigator and a fellow of the American Physical Society. And on a more personal note, Senthil has always been a source of great motivation and inspiration for many of us who were his classmates at various points of time in his academic career. So it's really a great pleasure to have Senthil giving these lectures. So without delaying things further, I'd like to invite Senthil to give the first lecture.
Thanks, Kedar. Yes, it's a personal pleasure to come here and give these wonderful lectures. As some of you may know, I spent a couple of years in this institution about 10 years ago, and I made a lot of friends, and it's always a pleasure for me to come back to Bangalore. So let me thank Spencer and Kedar and Shubroto for putting this together, and in particular for inviting me to come and talk to you this week. So the title of my talk today is Non-Local Quantum Entanglement in Macroscopic Matter, and it's also the title of the program that of the discussion meeting that many of us have been participating in. So I want to tell you about some of the things that excite us in quantum condensed matter physics, which are informed by ideas from quantum information. Okay. What's going on? Neither of these seem to work. How to click there? Okay, very good. That works now, right? So, so let me start with some brief remarks about entanglement and quantum mechanics. So entanglement is a fascinating and weird property of any quantum mechanical system that has some moving parts inside. So two parts, let's call them A and B, of a quantum mechanical system could share this property called entanglement. So let me illustrate what this is with a simple example. Let's think about the spin orientations of two electrons in a simple molecule, a two-electron molecule. So the two spins, A and B, could be in such a state, in which case we would say that they are unentangled with each other. What that means is that each spin is by itself in a definite quantum state. So here I can look at any particular spin and say what state it is in. And this should be contrasted with the different possible state of this two-electron molecule, where the two spins form some such, or in some such state, where A is up, B is down, and that's superposed quantum mechanically with the other possibility where A is down and B is up in some way, with either a plus sign or a minus sign. So in this second case, in a state like this, we say that the two spins are entangled with each other. Then each spin is by itself not in a definite quantum state, even though the full composite system of these two electrons, of the two spins, is in a definite quantum state. So the full system is in a definite quantum state. But if you ask me about the quantum mechanical state of a single spin, there is no definite quantum state that it is in. So Schrodinger, long back, allegedly, actually he really said this. He said they would not call entanglement one, but rather the characteristic trait of quantum mechanics, and the one that enforces its entire departure from classical lines of thought. So this is a very strong statement coming from one of the founders of quantum mechanics. Right? Now it's interesting for the students in the room to, you can't debate the fact that Schrodinger actually made this statement, but it's interesting for you to debate whether this is actually a correct statement or not. Right? Okay. So what entanglement is about is the relation of a part of a quantum mechanical system to the whole system. If in this example of this two-spin molecule, two-electron molecule, the two spins are in such a state so that the wave function is unentangled, then the wave function of the whole system factorizes into a product of the wave function of the components of the system. Okay? So other examples would be a state like this, where A is up and B is down, or even a state like this, where A itself is in a superposition of up and down, but it's the full composite system is its wave function still factorizes into a product of definite quantum wave functions for each part. Okay? In contrast, if the two parts of the composite system are entangled with each other, then the wave function of the full system does not factorize as products of wave functions of the parts. That means that you cannot describe any one part of the system fully quantum mechanically without describing the full system. Okay? So what I'm interested in, and what many of us that are here for this discussion meeting are interested in, are not simple molecules or small quantum systems, but we're interested in macroscopic quantum matter, where we have a large number, order 10 to the 23, interacting degrees of freedom, which must all be treated quantum mechanically. So an example, a classic example in solid state physics is the electrons inside a macroscopic piece of metal, like copper. For an ordinary metal, for the electrons inside an ordinary metal, even room temperature is cold, and one of the things that we are taught as students of solid state physics is that the electron motion inside a piece of copper at room temperature should be treated quantum mechanically rather than as thermal motion. Okay? So let's now ask the following question about entanglement, quantum entanglement in the quantum mechanical system that's presented to us by macroscopic matter, like, for instance, electrons inside a piece of copper. So how are the different parts of a piece of macroscopic matter entangled quantum mechanically with each other? Right? It's a natural question to ask about any composite quantum system, so let's ask this about this gigantic composite quantum system. So it turns out this question is very deep and very fundamental, and its importance became clear only in the last few years, though the question itself could have been posed any time in the last many, many decades. And it turns out that it's been very fruitful to pose this question in our current attempts to understand and describe various kinds of phases of matter, some of which I'll mention as we go along. So before I do that, let me sort of give you a lightning review of condensed matter physics in like 3 slides. So phase of matter, so one of the big ideas in condensed matter physics is that macroscopic matter in equilibrium organizes itself into phases. We have solids, liquids, and gases, the phase of high school physics. And we learned that a magnet is in college, we learned that a magnet is in a new phase of matter by itself. Likewise, a superconductor is a new phase of matter, so on and so forth. So one of the big achievements of 20th century condensed matter physics is the development of new organizing principles that help us describe the multitude of phases of matter. And these principles center around these 2 phrases, the concept of long-range order and the associated concept of broken symmetry, which I'll describe in the next few slides using various examples. The classic example is a crystalline solid in which the atoms have arranged themselves into an ordered array, right? Something like this. Now, when you look at a pattern of atoms which looks like this, the first thing you'll recognize right away is that the pattern of atomic positions in some small region immediately determines the atomic positions far away. Right? So the pattern just keeps repeating. So just look at one small corner of this pattern, you know what's going to happen far, far away. So this crystalline solid is an example of what physicists call a broken symmetry. So the microscopic interactions between these atoms, whatever atoms make up this pattern, are typically invariant and are translating all the atoms. But this particular state in which the atoms are frozen into this pattern, this particular equilibrium state is obviously not invariant and are moving all the atoms by some infinitesimal amount. So this particular state does not share that the atoms are frozen into, does not share the symmetry that underlies the laws that describe the interactions between the atoms. Okay? So that's the concept of broken symmetry. Now, this notion of broken symmetry has a number of general consequences for the properties of macroscopic matter, which in the 20th century were recognized to be huge, powerful, unifying principles for thinking about ordinary matter. So the pattern of broken symmetry determines many, many macroscopic properties of ordered matter. Again, in the context of a crystalline solid, the classic example is the rigidity of a solid, which can be understood in very general terms as a consequence of the broken symmetry. And it turns out that the persistence of currents in a superconductor, the very property that defines the superconductor, is closely can be understood within, as the same kind of phenomenon as the phenomenon that associated with the rigidity of solids. Right? So in that sense, the broken symmetry point of view is a unifying theoretical framework that enables you to think in some common language about a vast variety of phenomena. So let me illustrate this with magnetism. So the most familiar form of magnetism is ferromagnetism. It was allegedly discovered around 600 BC, at least according to Wikipedia, so it must be right. We now know that the microscopic picture of what's happening in a ferromagnet is that the electron spins inside the magnet are all pointed in the same direction. So this is an example of a broken symmetry. The interactions between the spins typically do not pick a direction for the spin, but this macroscopic magnetized state has a specific spin orientation. Okay? So this is an example of the same phenomenon that you see in a crystalline solid. Here spin symmetry, spin rotation symmetry is broken spontaneously in the ferromagnetic state. Now, actually the more common form of magnetism is what's known as anti-ferromagnetism. It's not ferromagnetism, though ferromagnetism is more familiar to a non-physicist. So in an anti-ferromagnet, the spins are still frozen, but they freeze into a pattern which oscillates in space. And this state too breaks spin rotation symmetry because any given spin has a frozen orientation, just that the pattern oscillates as a function of space. So it breaks spin rotation symmetry, but there's no net magnetization because the magnetic moments from all these spins cancel out. Now, it's one of the remarkable facts of the history of physics that antiferromagnetism, despite being much more common, was only discovered in the 1930s, though ferromagnetism, despite being much less common, was discovered in 600 BC. Right? So what's going on? Why did that happen? Right? And the reason is very simple. Ferromagnetism is easily detected. The probe that you need is just a piece of metal. You bring it close to a ferromagnet and you know whether it's a ferromagnet or not. In an antiferromagnet, the spin orientation oscillates on an atomic length scale. So to really demonstrate that something is an antiferromagnet, the probe that you need is something that should sense the atomic spin with microscopic resolution, with say angstrom resolution. Right? We didn't have those probes till the 20th century. Right? So there's perhaps a lesson here that simply because some state has not shown up with the probes that we currently have doesn't mean it's not very common. Okay? So how should we describe quantum mechanically these magnetic states of matter? Now, the essential properties of these two magnetic states that I've described so far are contained in their ground state wave function. And let's write down prototypical ground state wave functions for either of these phases. The ferromagnet, we'll just write down a wave function where all the spins are up. And for the antiferromagnet, we'll write down some such oscillating pattern. Now, what do these prototypical wave functions actually capture of the true quantum mechanical ground state of 10 to the 23 interacting spins? Right? So what they actually capture is the pattern of broken symmetry. And since the pattern of broken symmetry holds the key to many of the macroscopic properties of the magnet, any wave function that captures that pattern is a good prototypical wave function. Okay. Okay. Now, it's important to make several observations about this quantum mechanical description of magnetism. In both these cases, to determine the pattern of broken symmetry, we only need to look at a small part of the full system. I've only written down what the few spins are doing, but you'll immediately guess that in this first case it's a ferromagnet, that in the second case it's an antiferromagnet. So the information on the pattern of broken symmetry is stored locally in the ground state wave function. The more precise way of saying that is that these prototypical wave functions are short-range entangled. So let me describe what that means. So these wave functions are clearly product wave functions where each spin which is a part of this big quantum mechanical system is itself in a definite quantum mechanical state. So this is a product wave function. Though it captures the broken symmetry, it is a product wave function, and likewise for the antiferromagnet. That means that in these prototypical wave functions, there is no entanglement between the different spins that make up this macroscopic system. Okay? Now a more general wave function, which is still in the same phase, but is not the simple prototypical wave function, will not have exactly zero entanglement between different spins, but the entanglement will be short-ranged in space. Okay? So these wave functions, so these states, the ferromagnet and the antiferromagnet, are examples of states with long-range order, but these are states that don't have any long-range quantum mechanical entanglement. Okay? So most of the history of magnetism, certainly since in the modern era, since the discovery of antiferromagnetism, has consisted of the elaboration of broken symmetry and other states which are also short-range entangled. Okay? Now an important fact about broken symmetry is that it's what enables classical physics to emerge in a macroscopic system. So all of us learn that quantum mechanics is the right description for small systems, but once you start talking about big systems, that classical description becomes more and more legitimate. So what guarantees that is the concept of broken symmetry. So once you have a broken symmetry, there's a macroscopic description, a classical macroscopic description in terms of whatever it is that orders. For example, in a ferromagnet, the spontaneous magnetization becomes essentially a classical variable because all these spins are pointing in the same direction, and so the tiny quantum mechanical fluctuations of each individual spin gets washed out when you talk about the common orientation of all the spins. So it's the broken symmetry that guarantees the emergence of classical physics in a macroscopic system. So what I want to talk about in today's lecture, and what many of us are talking about through the discussion meeting, of states such as the one that I'm just going to describe. So particularly in the last 10, 15 years, there's been the discovery experimentally of a qualitatively new kind of magnetic matter, something that's totally different from anything that we've known in the previous 2,000 plus years of the history of magnetism. And the popular name for this new state is a quantum spin liquid, and the prototypical ground state wave function for this state is not a direct product of local degrees of freedom, unlike, say, a ferromagnet or an antiferromagnet, but instead is something much more complicated, and it's much better thought of as a quantum mechanical superposition of, for instance, various kinds of fluctuating loop-like degrees of freedom, which cannot be deformed into product wave functions in any limit. So in these states, so what's really different about these states is that the quantum entanglement is long-ranged in space. So in the last 10 plus years or so, what humankind has discovered is this new state of magnetic matter where the entanglement, the quantum mechanical entanglement, is long-ranged in space. Okay? So we're used to dealing with the concept of long-range order and broken symmetry, but here there's a new kind of concept that's required to describe these states, and that's long-range quantum entanglement with or without long-range order. Okay? So what is a quantum spin liquid? So a rough description is actually it turns out in retrospect there's a bad description, but it's rough. It sort of gives you the rough idea. Is that the spins do not freeze into any pattern, but fluctuate in time and space due to quantum zero-point motion. So that's why it's called a liquid of spins, unlike an antiferromagnet or a ferromagnet. So So in terms of a quantum mechanical wave function, the idea is that each spin forms an entangled pair, a spin singlet with some other spin, and in any one configuration, one piece of the wave function will involve taking all the spins in your, inside your solid and pairing each one up with some other spin into a spin singlet, and then allowing these spin singlet configurations to resonate with each other, much like there's resonance in benzene. So this kind of state was envisaged by Phil Anderson, first in 1973, and later applied to IISc superconductivity in 1987. And I believe he conceived of this explanation of this application to IISc superconductivity right out here in Bangalore when he was visiting for some conference in December 1986. Professor Ramakrishnan can tell you more about that story. So what I'm going to talk about is a lot of Bangalore connections. And apparently there's also older suggestions of polling going back to the 1950s. So what's interesting about these long-range entangled phases? So if the entanglement is long-ranged, then the universal information about the state is not visible by looking only at a small part of the full composite quantum mechanical system. Okay? Since once things are entangled, you can't describe a part of the system fully quantum mechanically without describing the whole system. And the passage from microscopic to macroscopic scales is not associated with the emergence of classical physics, in total contrast with a broken symmetry phase, for instance, the ferromagnet. Right? So all these things that we learn about macroscopic systems, which relied implicitly on there being some sort of broken symmetry, we now have to revisit. And the spin liquid state that I mentioned is not, in fact, the first or even the most familiar example of a long-range entangled state, but it's a very topical example. There's an older, very famous example, which many of you have probably heard about. It's called the fractional quantum Hall state. I'm not going to talk about this at all, actually. But this was discovered in the early 1980s, and it's a precursor to the conceptual precursor to the quantum spin liquid state. Now, even this is not the very first example, and there are other fascinating examples associated with metals. In fact, it turns out that a metallic ground state of electrons, which for conventional metals is described by what's known as a Fermi liquid state, is in fact the oldest and most familiar example of a long-range entangled state. So the free Fermi sea, which describes a metal, is already an example of a long-range entangled state whose non-triviality perhaps was not really appreciated by humankind till we started thinking about all these other exotic phases of matter. And now, of course, and one of the things that's going on in condensed matter physics is that there are many new metals which are metallic, but which are not described by the standard theory known as Fermi liquid theory. And for lack of a better word, they're known as non-Fermi liquids. And these are also examples of long-range entangled states. So the studies of these kinds of states, quantum spin liquids, quantum Hall states, Fermi and non-Fermi liquids, is a big part of modern quantum condensed matter physics. And it's really the unifying common theme is that these are studies of phases, of quantum phases with long-range quantum entanglement. So let's return to spin liquids. So can quantum spin liquid phases exist? So this is a question for theoretical physicists, right? So is such a phase allowed to exist? And the answer is yes, and there's many, many people involved in demonstrating that this is the case, some of whom are in the room. Based on this theoretical work, it turns out that it's become clear there's many, many dramatic phenomena that are seen to be theoretically possible. So an example is that an electron, which is a fundamental particle in the vacuum of the universe, can, inside, regard as an excitation of a quantum phase, can, if the phase is long-range entangled, break up into fractions. Okay? Another dramatic phenomenon is that these pieces of the electron interact with each other through emergent long-range quantum mechanical interactions, even in situations where the microscopic interactions are just short-ranged. Okay? And the same kind of phenomenon was already established in the two-dimensional fractional quantum Hall effect, but we now know that it's possible under much less restrictive circumstances. So, do quantum spin liquids actually exist? That's not a question for theorists. Theorists had better stay away from answering that question. It's a question for experiment. And there's many, many interesting candidate materials that have emerged in the last few years, and some of which are being discussed at this meeting. So one example that I'll briefly mention is in a class of materials which are made out of long organic molecules which stack together to form a crystalline solid. In fact, these turn out to be the most convincing examples of spin liquids, of quantum spin liquids. There are some layered inorganic materials as well on weird lattices known as the Kagome lattice. The best example of these is a material synthesized some years ago by my former colleagues at MIT, Young Lee and Dan Nocera. So these two examples are both quasi-two-dimensional materials in which the magnetism, the magnetic electrons predominantly live in layers, and there's very little contact between different layers. There are also three-dimensional oxide materials, sodium iridium oxide. Here the iridium ion is magnetic and it forms a three-dimensional network, and many more. But these are some of the prominent examples. So let me describe some of the phenomena that have been discovered in experiments. So all these materials are electrical insulators. But despite this, it turns out that many properties other than electrical conduction are very, very similar to a metal. Okay? So I'll show you data with I'll show you two examples. One is a measurement of the entropy of the electrons inside this electrical insulator at low temperature, and the other is a measurement of the heat conductivity of this electrical insulator. Okay. It turns out that both these properties are measured to be extremely strange and unlike anything that's known to happen in any conventional insulator. Okay. So this is a plot of the heat capacity of this insulator divided by temperature, plotted as a function of T squared. Now, solid-state physicists in the room will recognize that this is the classic way in which you're instructed to plot data measuring the electronic heat capacity of a metal. The reason to do this is that there's always a contribution to the heat capacity coming from phonons, from lattice vibrations, which goes like T cubed. While in a free Fermi gas, the electronic heat capacity is proportional to T. So the standard plot is to plot C over T versus T squared and look for an intercept. Now, when this experiment was done in one of these organic insulators, what they found was that there's a T cube contribution, just as you expect from the phonons, which are always there. But there's also a non-zero intercept, exactly the way a textbook metal is supposed to behave. But this is done in an insulator. Right? So there's a linear T heat capacity in this insulator, much like there is supposed to be in a metal. Now, that kind of heat capacity can itself arise for a number of different reasons. The more dramatic experiment is a measurement of the heat conductivity. So what's plotted here is the heat conductivity divided by temperature at very, very low temperatures. Again, is a function of T squared. And the reason to do that is, once again, is to take away the effects of the contribution of lattice vibrations to heat conductivity. So once again, this curve for this particular material, DMIT 131, this is an abbreviation of what's already an abbreviation of the name of a long molecule. Right? An important thing to notice is that this plot, once again, has a non-zero intercept, which means that at very, very low temperature, the thermal conductivity of this insulator is linear in T. Again, when you learn solid-state physics, so one of the first things you learn is that the heat conductivity of a metal at low temperature is linear in temperature. So that's a classic signature of metallic thermal conductivity. Okay? So this electrical insulator is actually a thermal metal. Okay? In fact, it turns out it's a really good thermal metal. By combining these two measurements and with some of the intelligent estimates, you can estimate the mean free path of whatever it is that's giving you the transport in this material. And it turns out the mean free path is about 500 times the lattice spacing, even though the material itself is an electrical insulator. Right? So these are really dramatic experiments that show you that this material is doing something bizarre, something very weird. So what's going on? Okay, I should have put in a reference here. So an important idea towards understanding these experiments is contributed by Alexei Motinich, who's somewhere in the audience, right out there. So the low temperature properties of metals, we know from high school physics, are determined by mobile electrons obeying the Pauli exclusion principle. Now this material seems to behave much the same as a metal, except that it doesn't conduct electricity. Right? But in an insulator, there can't be mobile electrons. Otherwise, it would have been an electrical conductor. So a promising idea is that perhaps there are new kinds of emergent particles which obey Pauli exclusion and carry the electron spin, but not its charge inside these materials. Okay? And such phenomena are known to be theoretically possible in long-range entangled phases, but are prohibited if the ground state only has short-range entanglement. Okay? So let me give you a picture for how to think about this kind of phenomenon. Now, again, the high school description of a metal is a picture something like this. We have ion cores that are positively charged and that form a regular pattern, and there are mobile electrons that are swimming freely in the background of these ion cores. Right? So that's our picture of a metal. Okay? Now, in this insulator, the corresponding picture is that the electrical charge of these electrons gets bound to these ion cores to form a neutral entity, which is sitting there, and that forms the background, while the remaining piece of the electron is still swimming freely. Right? And the remaining piece is just the spin and the statistics of the electron. Right? So the challenge, of course, is how can this happen? How can the electron shed just its charge but retain the spin and statistics? Right? But the experiments are leading us to contemplate ideas of this kind. Okay? So theoretically, we know that there's no single quantum spin liquid phase, just like there's no single magnetically ordered state. There can be many, many different patterns of magnetic ordering. Likewise, there's a wide variety of distinct kinds of quantum spin liquid phases, each with distinct physical properties and different low energy physical descriptions. And a gross distinction that's useful to keep in mind is that sometimes these spin liquid phases can be such that all excitations in the phase are gapped. Sometimes they can be such, there are other spin liquid phases in which the excitations are gapless. And these gap spin liquids have many interesting properties. They are actually very, very well understood. I won't have time to describe these anytime in these 3 lectures, but there's a phenomenon known as topological order that captures these gap spin liquids. The gapless spin liquids are not as well understood. They go beyond this framework known as topological order, but they're in fact the ones that are relevant to current experiments, and it turned out to be very, very powerful platforms for understanding many, many phenomena in solid-state physics that people have grappled with for decades. For instance, phase transitions between metals and insulators and things of that sort. Okay, so in light of all these phenomena, and given that these kinds of phases can exist, what's the challenge for theory? So the challenge, one challenge for theory, the challenge that people like me are particularly enthused by, is to construct effective field theories of distinct quantum spin liquid phases or other similar long-range entangled phases and their associated phase transitions. Okay? So let me elaborate on what this really means. What do we mean by saying, why do we want an effective field theory? Okay? So let me make a few sort of remarks on effective field theory in condensed matter physics. Now you could say, if you were from a certain point of view, there is no real need for an effective field theory in condensed matter physics. We, after all, know the microscopic models that describe any given material to some reasonably good approximation in many circumstances. Since you may have a Hubbard model, a TJ model, or some lattice spin Hamiltonian. So we know the Hamiltonian to some approximation. So given that Hamiltonian, just solve it and describe experiments. Right? So that's one approach. That's not an approach that I myself often take, and certainly many of the people in the room who are participating in this meeting or also often don't take this approach. Rather, there's a different approach where you start from the microscopic model and argue towards some intermediate level description, which is not entirely faithful to the microscopic model, but captures enough of the essence of the microscopics that one can work with it. And the hope is that this effective field theory applies to a broad class of microscopic models, not just the particular one that we might have guessed. In particular, if we made a wrong guess, maybe we got some of the parameters wrong, maybe that doesn't matter so long as we use the right effective field theory. Okay? And then use this low energy effective field theory to make predictions about experiments and phenomenology. Okay? So if one can get away with this, there's a lot of value in doing that, but sometimes it's very hard to do this, and you have to go through this step. Even in situations in which you can do this, there's a lot of value in doing this, because doing this gives you an understanding of phenomena in which you see exactly how robust it is to fiddling around with the details of the microscopic description. Okay? So if you want to build an effective field theory of a phase, let me outline two criteria which I describe as the minimal requirements, the minimal challenge that any successful effective field theory should meet. So the first is that it should be tractable. It should be simpler to understand than the original microscopic model and to relate to experiments. Otherwise, what's the point? What insight have you learned? And for this purpose, continuum field theory is often useful, but it's often not necessarily of the kind that's familiar from high energy physics. So just knowing high energy physics usually doesn't help you solve condensed matter physics problems. So tractability is a practical criterion for a successful effective field theory, but there's a conceptual criterion which is really, really important, and which informs the scientific style, not just of myself, but I think of many of us who are participating in this program. And that's that this effective field theory must satisfy what I call the criterion of emergibility. So there's a lot of talk, there's a lot of discussion of the phenomenon of emergence in condensed matter physics, but I think there's the concept that I'm going to define of emergibility is a key concept that is just as important. Okay? So what is emergibility? So a proposed low energy effective field theory must at the very least be capable of emerging from microscopic lattice models in the right physical Hilbert space and with the right symmetries. Okay? So this criterion, it's obviously necessary that this be satisfied by any reasonable effective field theory that someone's proposing. And if this criteria is not satisfied, then this effective field theory is useless for this particular system. Right? So it's a minimal criterion. And oftentimes, in research, we are satisfied even if we are able to show emergibility without actually connecting to a specific microscopic model. Just show that it's capable of emerging in the right Hilbert space with the right symmetries. It turns out there's many, many examples of interesting low energy effective field theories which are not emergible, and I'll describe one such in tomorrow's lecture. So how should we show emergibility? So one approach to showing emergibility of a proposed effective field theory is to demonstrate that it can actually emerge through calculations on a designer lattice Hamiltonian, or a lattice Hamiltonian that you design for precisely the purpose of showing emergibility. So this wonderful phrase, designer Hamiltonian, was I learned it from Bander Sandvik and Ribu Kaul, who are both in the room, and I'm sure you'll see that phrase appear repeatedly in their talks. So these designer Hamiltonians do not need to be realistic to serve the purpose of proving emergibility. Okay? So as they are in the right Hilbert space with the right symmetries, they've done their job. Right? And then there's a much more complicated task of starting with a realistic Hamiltonian and then showing that this emergible theory has actually emerged in the realistic Hamiltonian. But that's a much more complicated task. Okay? So in conventional condensed matter physics, the way we describe them is predominantly through a Hartree-Fock approximation of an interacting system, and then including some fluctuations. And the structure of the effective field theory is that of Landau quasiparticles plus any broken symmetry order parameters if the system breaks a symmetry. For instance, if you're describing metals, the effective field theory is this Fermi liquid theory, and this was the designer Hamiltonian, familiar to all condensed matter physicists, known as Gilliam, is just a model of a free Fermi gas with Coulomb interactions in the presence of a positive uniform background. Superconductivity, the effective field theory is Landau-Ginzburg theory coupled to of the order parameter coupled to the Bogoliubov quasiparticles of the superconductor, and there's a sample designer Hamiltonian which is totally artificial, but it captures the essence of superconductivity. That's the reduced BCS Hamiltonian. Likewise, for an anti-ferromagnet, there's a field theory known as the nonlinear sigma model, and this is sample designer Hamiltonian, which is the simple nearest neighbor Heisenberg anti-ferromagnet. Okay, but what are the analogs of these theories for quantum spin liquids or other exotic phases? Okay, and in particular, what are the useful degrees of freedom for formulating an effective field theory? So it turns out, not surprisingly, the field theory is usually not in terms of electrons coupled to Landau order parameters. Rather, you need something else. So there's one approach that's turned out to be very, very powerful. It goes either in the name of slave particles or in more recent years, the name of partons. And the idea is to do something weird. It's to fractionalize the spin or electron into fractional pieces, and those fractional pieces are then coupled to fluctuating emergent gauge fields. Okay? So let me describe how this works. Just a few equations in this and the next slide. So in a spin system, what one would do is to write the spin, the quantum mechanical spin, represent that in terms of fermionic objects, which carry the spin of, represent the spin using fermionic degrees of freedom. So these fermions are often called spinons, and this representation, for it to be faithful to the underlying spin system, it requires that you constrain the Hilbert space of these fermions. So it's a redundant description. So for instance here, that you want to require that the number of fermions at each lattice site R is precisely 1 to ensure that you're in the physical Hilbert space. And that constraint then implies that this description is redundant, and in particular, you can change the phase of these fermions arbitrarily, and that doesn't affect the physical spin operator. Alternately, you can represent the spin using bosons, and there'd be a similar constraint and a similar redundancy. Okay? So you start by doing something weird. Right? Instead of working with the spin physical Hilbert space for spin system, you work in some redundant Hilbert space of, say, a fermion system or a boson system. Okay? And then because it's a redundant description, you have to, the physical Hilbert space is obtained by putting a constraint on this enlarged Hilbert space. And the strategy to gain access to these interesting long-range entangled states is to put, for instance, this fermion F in some mean field state with a quadratic Hamiltonian. You could play around with many, many different kinds of mean field states. A simple example would be to put these fermions into a metallic ground state of these fermions. Since I'm calling these fermions spinons, this is what would be called a spin-on metal. Just let these fermions hop on a lattice. And the resulting mean field description gives you a description of an electrical insulator whose spin physics is similar to that of a metal. Okay? Alternately, you could write down a Hamiltonian, a quadratic Hamiltonian for these fermions, which has an addition to fermion hopping terms, fermion pairing terms, in which case the spin physics that's described by this Hamiltonian will be very similar to the spin physics of a superconductor, even though we're now describing an electrical insulator. Okay? So this gives you a mean field theory for some highly non-trivial quantum spin liquid insulators which inherit the spin physics of either a metal or a superconductor, even though electrically they are neither metals nor superconductors. Okay? Now, as usual, we have to go beyond mean field and include some fluctuations. So the way we've set this thing up, our description had this big, was in a redundant Hilbert space with a constraint, which was described as a gauged redundancy, because we could make some transformation locally at each site of the lattice. And typically, the mean field Hamiltonian will break this gauged redundancy down to some subgroup. So then when we do fluctuations beyond mean field, we need to couple these, for instance, these fermions F to gauge fields that live in that subgroup. And that way, we'll derive an effective field theory for a putative phase of matter in terms of these weird variables, right? These spin-ons and fluctuating gauge fields, and the physical spin is related to these things in some complicated way. Right? The spin is some bilinear of these spin-ons and so on and so forth. Now, this effective field theory can then be used to address all kinds of properties of this putative spin liquid phase. For instance, its stability. Is this a stable field theory, or does it give you a stable description for stable phase of matter, or does it not? Right? And we can use it to predict testable physical properties. And an example, again, if we choose the spin-on metal band structure, then the effective field theory consists of a theory in which the spin-ons are formed a Fermi surface, and this Fermi surface of spin-ons is coupled to a fluctuating U1 gauge field, and likewise in this paired spin liquid case. So this theory, for instance, can be used and has been used in literature to try and make predictions for, say, these organic spin liquids that I described a few slides back. So that's all that I'm going to say about the slave particle framework. So let me make some comments on it. So again, for some of the older solid-state physicists in the room, this would seem like there's something that they would definitely be familiar with. People have been trying to do this in the field for nearly 3 decades now. But the slave particle framework, at some intermediate stage in history, fell into a lot of disrepute because it was assumed that what it was trying to do was to solve particular microscopic models reliably. Okay? Now, if you take that point of view, then there's a lot of criticism that can be heaped on this framework. But I think that's not the right point, the useful point of view. And the useful point of view is to regard this framework as a way to construct an effective field theory of many exotic phases and their phase transitions that are beyond standard quasi-particles. Right? The big advantage of this framework is that the resulting effective field theories are emergible, and and they are often tractable. Okay? So they satisfy these minimal criteria that I described for what a reasonable effective field theory should do. Right? So let me emphasize that the main advantage of the slave particle framework is that they give us a handle, a theoretical route to obtaining a sensible effective field theory for a possible phase of matter. Okay? And there's many things that have been done within this framework. And there's some successful contact with experiments. In fact, the entire theory of the fractional quantum Hall effect can be described within this framework, as can the theory of the Hoffield-Landau level and several quantum spin liquid states. Now, there's an open question in the field, which I myself am particularly interested in, but I don't know the answer at all. I don't think anyone knows the answer. Is whether this is the only framework that exists to obtain a sensible effective field theory for a quantum spin liquid phase, or whether are there quantum spin liquid states that are beyond the slave particle framework. Okay? The answer to that question is not known. There's some interesting hints based on experiments on metallic systems that there may be new kinds of phase and phase transitions beyond slave particles, but so far we don't have any examples. Okay, so that's sort of a general overview of states with long-range quantum entanglement. In the remaining time, I want to focus on a couple of questions that I will of fundamental importance and right now in the field, and that will connect very directly to my talks on Wednesday and Thursday. So the first is the interplay between symmetry, physical symmetry that may exist in a given system, and long-range entanglement. So once you have long-range entanglement, it's quite natural that physical global symmetry may be realized in a highly non-trivial way. Okay? The simplest example there is the phenomenon of fractional charge in the quantum Hall effect. So what do we really mean by fractional charge? Right? So fractional charge refers to the quantum number of the excitation under the global U1 symmetry associated with charge conservation. Okay? So in the microscopic Hilbert space, all excitations must have integer charge because it's an electron Hilbert space. But once you go into a fractional quantum Hall state, which has this long-range entanglement, the excitations in this fractional quantum Hall state, the so-called Laughlin quasi-particles and quasi-holes, they are defects in the pattern of entanglement of the ground state wave function. Okay? Now these defects are not created by local objects, but rather they are created by non-local objects. So these things are not bound by the requirement that they don't live in the physical Hilbert space. They're not bound by the restriction that they necessarily carry only integer charge. So they're allowed to carry fractional charge, and indeed, that's one of the great phenomena in the fractional quantum Hall effect. So the fact that this fractional charge is already in the fractional quantum Hall effect is precisely the statement that global symmetry is realized in some highly non-trivial way by the excitations of the quantum Hall phase. And that phenomenon holds a variant of this phenomenon happens in all long-range entangled phases. And if you come to my talk tomorrow, you'll see that there's all kinds of open questions and surprises there. Now it turns out there's a simpler question that I myself spent most of the last 2 years thinking about, as have some other people in the room, or Leszek Motrynich, for instance. So in the previous slide, I talked about how symmetry may be implemented in some non-trivial way in long-range entangled phase. Now it turns out that symmetry already has highly non-trivial effects even in short-range entangled phases, and physical global symmetries we now know may protect distinctions even between short-range entangled states. So this realization was forced upon us in a dramatic way by the discovery of topological band insulators made by Joel Moore, who's also somewhere in the room, and many other people in the last 10 years or so, and older phenomena in quantum magnetism. And the class of states of matter represented by these two examples is what's come to be known as symmetry-protected topological phases. These are not these exotic long-range entangles, and they're short-range entangled phases, but with a small twist coming from the way in which symmetry acts on these states to protect some aspect of entanglement in them. So surprisingly, despite being short-range entangled, studying these states has generated a huge amount of conceptual insight into these more complex long-range entangled phases. So a lot of the progress that I'm going to describe tomorrow in one example of this issue of symmetry and long-range entanglement would not have been possible without all the developments in understanding topological insulators and their generalizations. Okay? And topological insulators themselves are not long-range entangled, they are short-range entangled states. Okay. Okay. So the other conceptual area, the other area in which there's been a lot of interesting progress, and which again I'll give some examples of in my talk on Thursday, is various kinds of novel continuous quantum phase transitions. So once we recognize that there can be new kinds of quantum phases which are characterized by the entanglement structure rather than by their long-range order, there's long-range order and short-range order. That's there as a way to distinguish phases. But we're now saying that there's also long-range entanglement and short-range entanglement. Right? So clearly, the kinds of different phase transitions that can happen is enormous. Right? Once you include interplay of long-range order and long-range entanglement. So for instance, the simplest examples of phase transitions, quantum phase transitions, are the ones that cover that. I guess Subir is not here, but he'll show up tomorrow. Make up more than 50% of Subir Sachdev's book on the subject, or phase transitions like these, where you go from a phase with long-range order to a phase without any long-range order. For instance, described by a transverse field Ising model, but neither phase has long-range entanglement. And this example is the one in which the Landau-Ginzburg-Wilson paradigm of phase transitions actually works. In fact, it's the only example. There's many, many other examples of phase transitions that we can contemplate. For instance, ones with long-range entanglement going into phases without any long-range entanglement, with or without long-range order. Long-range entanglement and long-range order could coexist with each other, or they can exist independently of each other. Or you can have phase transitions between two different kinds of long-range entangled phases. Classic experimental examples of phase transition between two fractional quantum Hall states, the plateau transition. Finally, there's a weird example that some of us stumbled upon some years back. It's a phase transition, again, between two phases with no long-range order, but where the two phases, no long-range entanglement, but where the two phases have different patterns of long-range order. So except for this first example, in none of these other examples does the Landau-Ginzburg-Wilson paradigm work. And clearly, we need new ways of describing these phase transitions as well. So let me make a remark on this last example. So in all these previous examples, except for the standard one, in all these other cases, at least one of the two phases on either side of the phase transition has long-range entanglement, and long-range entanglement is not captured by a Landau order parameter, so you can't have a Landau-Ginzburg-Wilson description. So that much is obvious. Right? Now in this example, it's a Landau forbidden phase transition between two Landau allowed phases. So the phases on either side have a Landau description, a description in terms of Landau order parameter. They're not long-range entangled. Nevertheless, the phase transition is not Landau allowed, and the Landau-Ginzburg-Wilson paradigm breaks down, and there's a need for a new kind of description. Right? And in this case, we have many examples of this kind of phase transition, what have been called deconfined quantum critical points. And I believe there'll be at least one or maybe two talks on this apart from mine later on in the program. Okay, so let me conclude with by talking about what the future might hold. In the short term, what we need is clearly a combined theory experiment effort to characterize, for instance, currently existing quantum spin liquids and both in theory and in experiment, and other long-range entangled phases. A pressing need is in the theory of non-Fermi liquid metals, for which there's zillions and zillions of experiments and almost no theory. More ambitiously, we might hope that there may be a direct demonstration of non-local entanglement in experiment. So right now, what we know are the symptoms of long-range entanglement. We know what kinds of weird excitations the system can have, but we would like to have a way of directly probing the ground state experimentally and demonstrating known local entanglement. The theory predicts a bewildering variety of such exotic phases, even in magnetic matter. Right? So it's a long set of challenges for experimentalists, even based on what we already know. More exciting, perhaps, is the long-term prospects. So in the last 3 decades, there have been many, many dramatic experimental discoveries in this whole field of solid-state physics. So all of the things that at least I learned in textbooks have all been dethroned. Right? So some of these things that have been discovered, the fractional quantum Hall effect in 1982, high-TC superconductivity in 1987, strange metals where the charge carriers are not simply individual electrons, these quantum spin liquid magnets. So some of these we understand, like the quantum Hall effect, but most of these we don't understand. Right? Together, what all these discoveries have done is to open our eyes to a non-classical macroscopic world where at macroscopic scales, classical physics does not emerge. Broken symmetry is not the concept that describes these phases. Rather, there's something that's truly quantum mechanical that describes the macroscopic properties of these kinds of phases and the associated phase transitions. So the challenge for us is to characterize these various patterns of entanglement in macroscopic quantum matter, and that challenge promises to be as educational and as entertaining as a previous century's effort at characterizing patterns of broken symmetry. So let me stop there. Yeah, sure. It certainly is beyond Landau theory because, so within Landau theory, what you would do is to say that the order parameter is king, everyone else doesn't matter. Now, if you have a phase transition, say a Stoner transition in a metal, people have known this for decades. That you obviously can't ignore the electrons. Right? And the early attempts to describe that phase transition tried to do away with the electrons by treating them as a dissipative bath, but we now know that those things are not quite right. Right? So, in fact, a lot of those problems are not fully understood, and as you know, they're in the process of being discussed.
Yeah, 2 slightly crazy questions. The first one is, you said about, so in the spin liquid, the quantum spin liquid case, you had the charge sort of separated out from the spin, and I was just wondering whether, but the spin carrying objects were still fermions. They were, but can you, in this enlarged sort of Hilbert space picture, is it possible to have the spin and statistics also decoupled?
Sure,
that's also, there are examples where you can, but the physical objects will obey the spin statistics. This thing. Okay, so that was the first question. And the second one was whether the fact that since entanglement manifests itself on this macroscopic scale, do some of these systems, could they shed perhaps some light on some of the interpretational issues of quantum mechanics?
Anything is possible. Which means that I don't know.
Okay. So earlier, I think you mentioned that gapless spin liquid and gapped spin liquid. So which gap you are talking about, the spin gap or charge gap?
Oh, these are all electrical insulators. They have a charge gap. But when I say that something is gapped, it's a gapped spin liquid, everything is gapped. Right? There's no excitation.
Spin and charge, both modes are gapped.
Spin, charge, everything is gapped.
You have a spin gap, you have a charge gap.
That's right.
So
But in the gapless spin liquid, the charge is still gapped, but the spin fluctuations are gapless.
That I understood. So suppose I do a suppose I go from a mod insulator to a spin liquid insulator in which both charge and spin are gapped in both cases. Now suppose I tune a parameter. So at the transition from mod insulator to spin liquid insulator, you will see what? You will see a coherence length diverges or something? Or how would you characterize
Yeah,
that?
by a Morton insulator, I presume you mean, say, an anti-ferromagnetic Morton insulator.
Yeah.
Right. So the question you're asking is about the nature of the phase transition between an anti-ferromagnetic insulator and a spin liquid insulator.
Yeah.
Right. So at that kind of phase transition, the spin gap coming from the spin liquid side,
Yeah.
the spin gap will close. Right at the critical point, you will have gapless spin fluctuations. Okay. And associated with that, there will be a diverging spin correlation length coming from the spin liquid side,
Yeah.
which will diverge as you approach the critical point.
And then they will start to entangle in a singlet or something in the other side, in the spin liquid side.
Right. So far as describing what happens when you come from the spin liquid side. So when you come from the spin liquid side, the spin gap will close, and you'll have
But is
critical.
there anything going to happen in the coherence length or
coherence length? What is
of
coherence
the
length?
spin up, spin down states if they are entangled? So in the order state, they are also entangled in some sense, right?
No, so the many body wave function in the ordered state,
Yeah.
its long distance description is in terms of this product wave function. Right? So that's the right caricature of the ordered ground state. Right?
Okay.
So
Yeah.
there's no long range entanglement.
Maybe you have to
It
understand.
turns out that particular phase transition is really very well understood. In fact, my very first paper in life was about precisely that phase transition.
You said spin liquid, so there is no spin ordering, right? So there's no magnetic ordering. So does it mean that it
That's
actually
the simplest example, but I said long range entanglement and long range
Right.
order can coexist with each other.
Yeah. So my question was whether that means that intrinsically spin liquids will preserve time reversal symmetry.
No, not at all. There are many proposed spin liquids where, in fact, one of the earliest proposed spin liquids spontaneously breaks time reversal. But you could take a spin liquid material, say this organics, and subject it to a small magnetic field, and you won't destroy the spin liquidity. Indeed, in experiments, for instance, the thermal conductivity, the metallic thermal conductivity in the spin liquid is in fact enhanced by a magnetic field, rather than it doesn't go away in a magnetic field.
Sorry, this might be slightly technical and maybe it's just confusing, but so there's long-range entanglement and short-range entanglement, and there's gapped spin liquids and gapless spin liquids.
Right.
So gapless spin liquids are the ones with long-range
No,
entanglement.
all quantum spin
all
liquids
quantum
have
spin
long range
liquids
entanglement. The pattern of long range entanglement
is different.
is different.
Okay.
I have a question, if
Yeah.
you don't mind. So you wrote down some effective Hamiltonians in terms of the
Right.
auxiliary F
Right.
field, actually. Is there some way in which you can derive these from the original spin Hamiltonian derivation?
Yeah, so there are examples. There are examples where you
Is there
can.
any systematic
Yeah. There are exactly. For all this by now, many of these phenomena can also be demonstrated through exactly soluble models and things of that sort. That's more as reassurance. Right? So the more general thing that you want to do in situations where you don't have an exactly soluble model is to have an approximate but physically correct way of dealing with the system, right? Which is where this effective field theory is useful. But there definitely exist many examples where you can solve things exactly and check that these weird things that we do, writing the spin in terms of auxiliary degrees of freedom and so on, actually work. Right?
I'll tell you what I'm asking. So if you have a Hamiltonian in terms of, like S1 dot S2.
Right.
So in terms of the auxiliary variables, it's a 4 fermion interaction.
Exactly,
It's a very
yeah.
complicated thing, actually,
Right.
to deal with.
Right.
That's why I was wondering how you, in general, can, arrive at the Hamiltonians you...
Right. So
I understand your argument, actually, that in soluble models is encouraging, but...
Right. So the key is, I think, that's why I spent a little bit of time on this philosophical slides, because so you could ask, given particular microscopic, let's say spin Hamiltonian, right? How are you going to treat some particular spin Hamiltonian? Right? So the methods that I described in terms of these auxiliary fields and so on, given a generic spin Hamiltonian, you want to know what phase it is in, I don't think that's the way to go. Rather, you're better off trying to solve that model numerically as accurately as possible. And there's a huge amount of effort going on right now to develop accurate numerical methods to deal with arbitrary spin Hamiltonians. For instance, you can try to put it on a strip and do this density matrix normalization group, things of that sort. Right? Now, what this auxiliary field method is useful for is to describe, to derive an effective field theory for a proposed phase, right? To give you an idea of what the possibilities are and to describe the universal properties of the allowed possibilities. Right? So it's a totally different purpose for which it's best suited. Right? Historically, people tried to use it as a tool to solving microscopic Hamiltonians, and there it's not very good at doing that. Yeah.
Just following up on Kedar's point. You use the phrase pattern of entanglement, and it was also your final slide.
Yeah.
What do you exactly mean by that?
Yeah. So in complete generality, it's hard to know exactly what one means, but in specific examples, we know exactly what we mean. For instance, for these various gap spin liquids, right? It turns out there's an infinite number of gap spin liquids, right? Even if there's no symmetry in the problem, right? So how do you distinguish two different spin liquids, right? Let's imagine the Hamiltonian has no symmetry left, right? You've broken all symmetries, right? There's still an infinite number of distinct phases. So what distinguishes these different phases? Right? Now, because they're different phases, the distinction must be there in the ground state wave function. Okay? Now, it turns out that there's, for instance, one measure of entanglement that you can use to partially distinguish these different phases. It's what's known as, it's something that you extract by calculating the von Neumann entropy of a subregion. It's known as the topological entanglement entropy. So then, for a gap phase in any dimension, the entanglement entropy of a subregion is proportional to the area. It's this area law. So the leading correction to that area law in two dimensions, for instance, is a universal constant, and that constant is a universal number that can partially distinguish these different phases. Now, more elaborate distinction comes from calculating the topological properties of the quasi-particle excitations. So that's captured in topological data known as braiding fusion data. Right? There's an S matrix and T matrix and so on. So that kind of information is also contained in the ground state wave function, and there are ways to extract that. And again, the way to extract it is to take the ground state wave function, make an entanglement cut, and look at the entanglement spectrum, and then do various manipulations with it. And people have written papers giving practical protocols for determining all this information from the ground state, all this topological data given the ground state wave function. But it's ongoing work. So the pattern of entanglement, meaning for these gap phases, it's some Berry phase, it's some non-abelian Berry phase. That's sort of captured in the ground state wave function. We have reasonable ideas on how to extract it. Now, in the gapless cases, it's a lot less understood, but
So the metal-like properties that you showed for quantum spin liquids will probably be seen only for the gapless cases, right?
Yeah, oh, absolutely.
Yes.
Yeah.
Okay.
Yeah.
So what will be the experimental signatures for the gap spin liquid? They won't be any different, at least the thermodynamic ones, from the band insulators, right?
Right. So you have to do other kinds of clever experiments. So it's like asking pre-20th century, how do you tell when something is an anti-ferromagnet? Right? Or whether you just dismiss that as a boring non-magnet. So you need the right probe. Okay. Right? Now, for some examples of these gap spin liquids, we have very good ideas on what sort of right probe can reveal the spin liquid order in that material.
So neutron scattering or something?
No. Neutron will not tell you because its all spin fluctuations are gapped.
I see.
So the standard probes of magnetism will not work.
Okay.
So I can give you an example. So one example is to use this scintillator to build a Josephson as the barrier for a Josephson junction,
I see.
and then study Josephson tunneling. And in some cases that may work, and you may see a Chorgy Josephson effect.
Okay, I think we can thank Senthil for a fantastic talk. Tomorrow at the same time, same place. Thank you. It's called a winning strategy. You don't know how to derive.